Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about the normal distribution and standardizing. All right, so standardizing allows us to compare one observation to another if they don't have the same parameters. That is, if their mean and standard deviation are different. So we do this by making the means equal to 0 and the standard deviations equal to 1. All right, so when we standardize, we get things that are called z-scores. The z-score formula is z is equal to x minus x bar over s, where x bar is the sample mean and s is the sample standard deviation. If I'm working with the population parameters, then it would be x minus mu, which is the population mean, divided by sigma, which is the population standard deviation. This helps us to compare by telling us how many standard deviations an observation is above or below the mean. All right. Canceling out the units gives us an idea of how common the value is or how unlikely it is. If the absolute value of z is greater than 2, we typically consider the value to be unlikely. All right, so if it's more than 2 standard deviations above or below the mean, then it's unlikely. All right, let's do an example. The heights of 18 to 24-year-old women have a mean of 64.5 inches and a standard deviation of 2.5 inches. We know a woman who is 69 inches tall. How does she compare to the rest of women in her age group? Calculate her z-score and interpret what it means. Okay, so z is equal to x minus mu divided by sigma. Okay, these are the population means and standard deviations that were given to us for women 18 to 24 years old. All right, so z is equal to x would be her height, which would be 69, minus mu is the population mean, 64.5, divided by sigma, the population standard deviation, which is 2.5. All right, so I can calculate this. This gives me 1.8. So the woman's height is 1.8 standard deviations above the average height of women her age. All right, we also know a man is 71 inches tall. Who is taller relatively? Men are known to be distributed with a mean of 67 and a standard deviation of 2.3 inches. Okay, so relatively speaking, who is further from the mean? All right, we know that 71 inches is more than 69 inches, but their z-scores is what I'm going to look at. So I'm going to plug in my x value, which is 71, minus my mean, 67, divided by my standard deviation, 2.3, and I get a z-score of 1.739. Okay, so the woman is slightly taller relative to the sex. All right, in a distribution of heights in a school with the mean is 66 inches with a standard deviation of 2.8 inches, which is more unusual, a student with a height of 63 inches or 73 inches, okay? So one's lower than the mean, one's higher than the mean. We want to see which one has more standard deviations away from the mean, meaning it'd be more unusual. So I'm going to calculate the two z-scores. So z is going to be for the 63, 163 minus 66 divided by 2.8, the value minus the mean divided by the standard deviation, which gives me negative 1.071. So when the value that you're plugging in is less than your mean, you're going to have a negative z-score. All right, my z-score for the 73 inches is going to be 73 minus 66 divided by 2.8, which is 2.5. All right, so that's 2.5 standard deviations above the mean. So if the student that is 73 inches tall is more unlikely because the absolute value of their z-score is greater. Their height is further from the mean. To be certain that you would be accepted to the college you want, you would need an SAT score of at least 1900. However, you took the ACT. What score would you need to get on the ACT to be accepted? All right, we know the mean and the standard deviation for both the SAT and the ACT. And we want to figure out the z-score that corresponds with that 1900 score on the SAT and figure out what value would I need to get on the ACT so that that has an equal z-score. All right, so for the SAT, if I want to find the z-score, it's going to be 1900 minus the mean 1500 divided by the standard deviation 250, which is a z-score of 1.6, which means at 1900, you're 1.6 standard deviations above the mean of 1500. All right, so for the ACT, I know that I want to have the same z-score of 1.6. I don't know what the value I need to get is, but I know the mean and the standard deviation. So my x value minus my mean of 20.8 divided by my standard deviation of 4.8. And I'm going to do some algebra, multiply by 4.8 on both sides, add 20.8, and I get 28.48. All right, the normal model. The normal model or normal distribution is a bell-shaped curve that can be used when the data is symmetric. That means it's relatively even on both sides. And unimodal. Unimodal means it has only one peak. It is a theoretical model, okay? It's not meant to fit the data exactly. So you can kind of see in this histogram, you can see that the bars are coming a little bit. Sometimes they're above, sometimes they're below. But in general, it kind of fits this bell-shaped curve. All right, some symbols that you need to know, like the notation. For a statistic, when we're working with a sample, the mean, we use x bar. We use S, sometimes S and a little like subscript X, SX, for the standard deviation. And then graphs would be box plots or histograms. So when we're working with a sample, we're doing a sample statistic. When we're working with population values, it's a population parameter. Right? The symbol that we used for the mean is mu. It's a Greek letter. And then the symbol that we use for standard deviation is sigma, another Greek letter. All right, and then the graphs for this would be a smooth normal curve or a skewed curve. All right, so we don't do like the exact when we're dealing with parameter population values, just a smooth curve. All right, the notation for a normal model, we use capital N, and then in parentheses we put the mean and the standard deviation with a comma between. All right, so here's my normal distribution. I'm going to put mu, my mean is right there in the center. And then as I move, I add one standard deviation to the right. I subtract one standard deviation to the left. And when I go out again, I add 2 standard deviations to the right, 2 standard deviations to the left, and then 3 and -3. Okay, so the majority of what you're going to see is only going to be 3 standard deviations plus or minus the mean. All right, the empirical rule in a normal distribution says that 68% of the data falls within 1 standard deviation of the mean. 95% of the data falls within 2 standard deviations of the mean, and 99.7% of the data falls within 3 standard deviations of the mean. All right, so the majority of it is clumped right there in the center, which makes sense because you have the highest peak there. All right, normal percentiles. So if you're trying to find the normal percentile without a calculator, you're going to have z-tables. You're going to have front and back paper for z-tables. So convert the data to z-scores, then you'll use the z-table. So let's say your z-score is 1.80. You go to 1.8 on the left side, and then you go to 0.00 on the top, and you go down and across until you find the percent that matches. If you're using a calculator, you don't have to convert it to z-scores first, but you can if you prefer that. You go to second distributions, and then normal CDF. So it's like second, and then bars is the button. That's your distribution menu. You'll go down to normal CDF, and then you'll enter in your lower bound, your upper bound, your mean, and your standard deviation. And it'll give you the percent. If you're working backwards, okay, so finding the z-score from the percent can be done using the table in reverse. Okay, so let's say you know that the percent is 96.41. The problem with this is you don't usually get 96.41. You might get like 96, and so you have to find the one that's closest to that. And sometimes there's quite a few that are around there. So you got to pick the closest one, and you have to look at the whole table. So it is a little bit more challenging if you're using the table method. And then you'd go out, and you would get 1.80. You could also use the inverse norm function in your calculator. So the exact percentile may not be in the table, so you're going to try to just get as close as you can. And then inverse norm always goes from the left. Your calculator, if it doesn't give you the option to choose left, right, or center, which some things will give you that option, then it's automatically going on the left direction. So if you can think about that normal curve, if we shaded part of it, it's always like that left side automatically, unless it gives you the option to pick the right side or the center section. All right, suppose scores on an IQ test can be modeled normally with a mean of 100 points and a standard deviation of 16 points. Draw and label the normal distribution. All right, so I'm going to use my notation. It's capital N that says I'm working with a normal model. My mean is 100 and my standard deviation is 16. I'm going to start by putting 100 directly in the center. As I move to the right, I'm going to add 16 each time. As I move to the left, I'm going to subtract 16 each time. All right, and then again, I'm going to add 2 times 16 or add 16 to the one I just had before, subtract 16 again, and I get these values here. And then one more time, I'm going to add 3 standard deviations to the mean and subtract 3 standard deviations from the mean to get those values. All right, using the same setup with the IQ test with a mean of 100 and a standard deviation of 16 points, what percent of people scored over 123? All right, so I can find the z-score. Z is 123 minus 100 divided by 16, which gives me a z-score of 1.4375. All right, so if I'm doing this on the left tail, the probability that x is less than 123 would be equal to the probability that z is less than 1.4375. So again, remember if you're using the tables, you have to be using the left tail. So you have to find the probability that it's less than that z-score. So if you're using the table, you'd have to use a z-score of 1.44 because it only goes to the hundredths place, and you would get 92.51. But I want over 123, so the probability that x is greater than 123 is 1 minus the probability that it's less than 123. So I would do 1 minus 0.9251, and I'd get 0.0749. So 7.49% of people scored over 123. What percent of people scored under 94? All right, so I'm going to find the z-score. 94 minus 100 divided by 16 gives me negative 0.375. All right, so because it's under, it's already on the left side. I want to find the probability that x is less than 94. So that's equal to the probability that z is less than negative 0.375. Again, in my tables, I'd be using a z-score of negative 0.38. And I get 0.3520, or 35.2. What percent of people scored between 90 and 110? So I have this normal model, again, with a mean of 100, standard deviation of 16. I want to be between 90 and 110. So the probability that x is between 90 and 110. I could do my calculator for this one, or I can find the z-score at 110 and find that percentage. I can find the z-score at 90 and find that percentage that's below, and then subtract the two to find that in-between section. In my calculator, if I want to do in-between, I'm going to go to normal CDF, so second VARs, which pulls up your distribution menu, normal CDF. My lower bound would be 90, my upper bound would be 110, my mean would be 100, my standard deviation would be 16. That gives me 0.4680, or 46.8%. All right, again, the same situation, mean of 100, standard deviation of 16. What is the chance that someone scores over 120? So here's my normal model. I'm going to go to 120, shade above. Okay, so if we're going to use the calculator notation, you need to make sure that you are also drawing a picture, you're labeling, you're using a proper notation, and any calculator notation that you use, you have to label, like, what did that number, like normal CDF, and then what were those numbers you plugged in. So lower bound, upper bound, mean, standard deviation, you need to say what those numbers represent, because we are not everybody uses the same type of calculator, so they may put them in different orders. All right, so when you're trying to get points on your AP exam, make sure you label everything. So normal CDF, my lower bound would be 120. My upper bound would be positive infinity, which we can't type in, so we're going to put 99999. You can also do 1e to the 99 if you prefer that. The mean is 100, and the standard deviation is 16. That gives me 0.1056, or 10.56%. What is the chance that someone scored less than 80? All right, I'm going to draw my picture again. So here's my normal model. The mean is 100. I'm going to go to where 80 would be and shade below. I want to find the probability that x is less than 80. So I'm going to do a normal CDF. My lower bound would be negative 9999 or negative 1e99. Upper bound 80, mean 100, standard deviation 16. And that gives me 0.1056 or 10.56%. Okay, you can kind of see that those were the same number of standard deviations. One was above the mean, one was below the mean. So you're going to get the exact same percent. Okay, so if I calculated the z-scores, this one had a z-score of 1.25. This one had a z-score of negative 1.25. And because it's a symmetric model, the area under the curve is going to be the same on both sides if they're equal distance from the mean. All right, another example, blood pressures of high school students are normally distributed with a mean of 170 and a standard deviation of 30. Sketch the normal curve. So I'm going to put my notation, capital N, and then 170, comma 30. 170 is going to go in the center. I'm going to add 30 each time I move to the right. I'm going to subtract 30 each time I move to the left. What is the probability that a randomly selected high school student has a blood pressure of 180 or above? All right, here's my normal curve. I'm going to go to where 180 would be, and I'm going to shade above. So the probability that x is greater than or equal to 180, I'm going to do a normal CDF. Lower bound is going to be 180. Whoops, that should be a 180. Upper bound is 99999. Mean is 170. Standard deviation is 30. So I put that in. I should get 36.94%. What is the probability that a high school student has a blood pressure between 160 and 230? Right, here's my normal model. I'm going to shade where 160 to 230 should be. Make sure you label that. The probability that x is between 160 and 230. Do a normal CDF here. Again, make sure you're labeling. My lower bound would be 160. My upper bound would be 230. My mean is 170. And my standard deviation is 30. That gives me 0.6078 or 60.78%. What blood pressure has 25% of the observations below it? All right, so this time I have the percentage, and I'm trying to figure out what was that x value. So here's my normal model. I'm going to shade in about 25%. Probability that x is less than what gives me 25%. So because I know the percentage, I'm going to go to inverse norm. My area would be 0.25. My mean would be 170, and my standard deviation would be 30. Okay, and I get 149.765. If you wanted to use the table for this, you're going to look inside of the table for the percentage that's closest to 25%. Then you're going to go up and over, find that z-score. Then you'll convert that z-score to a value using the mean of 170 and the standard deviation of 30. Okay, so there's where that was, and we shaded below. So that section made up 25%. What blood pressure has 60% of the data above it? Okay, so probability that x is greater than what would give me a probability of 60%. Probability that x is less than something would also be equal to 40. So remember, your calculator always does on the left side. Your table always does on the left side. So if you were using the table, you'd have to find the area for 40 and then use the opposite of that to get your values. Some of your calculators will have the option to do left, right, center if it's an updated calculator. Some of you guys will have to do it with the 40. Okay, so If you have the outdated calculator, you're going to go to second vars, which is your distribution menu. You're going to go to inverse norm. For area, you'd put in 0.6, mean 170, standard deviation 30, and then to the right, because it's above, and so above would be on the right side of your curve. If you have an older calculator where you don't have that option, you do inverse norm. The area would be 0.4, mean is 170, standard deviation is 30. Because without the option, it always does the left tail. Either way, you should get the same answer of 162.4. All right, so 162.4 above. So this top one was 25%, this bottom one was 60%. What is the IQR of the blood pressure? So remember from the previous notes that IQR is the interquartile range, which is the third quartile minus the first quartile. So I have to figure out what is the value at the third quartile and the first quartile. So the third quartile is happening at the 75th percentile. So the probability X is less than quartile 3 is going to be 75%. So that third quartile would be 190.235. You can do an inverse norm there. Inverse norm area would be 0.75, mean would be 170, standard deviation 30. And that would be left or automatically if you're older calculator. Probability X is less than quartile 1 is 25%. It's at the 25th percentile for quartile 1. That works out to be 149.765. Again, inverse norm, area 0.25 this time. Here's what this would look like. Here's my normal distribution. My third quartile was at 190.2. My first quartile was at 149.8. I want the interquartile range, so that's the value between it. All right, I'm going to subtract it, and I want the value between those, so I get 40.47, which means that this in between here is taking up 40.47% of the data. All right, go Seahawks.